A single flaw in the newborn cosmos could have rewritten everything we see today. And number 1 is something almost nobody guesses, so stay tuned until we reach the very top of the list. Surprisingly, a vast, unusually cool patch in the cosmic microwave background stretches across about 5 degrees of the sky, a region scientists call the cold spot. First spotted by the WMAP satellite and later confirmed by Planck, this area is roughly 1.8 billion light-years across and appears about 70 microkelvin colder than its surroundings. While statistical flukes are possible, some researchers propose exotic explanations such as a supervoid, a massive underdensity of galaxies that could imprint a temperature dip through the integrated Sachs-Wolf effect. Others entertain far-out ideas like a collision with another universe, though evidence remains thin. Regardless of the cause, the cold spot reminds us that the early universe still holds secrets that defy simple models. Up next, we'll explore a deeper imbalance that still puzzles physicists.
Imagine a universe where matter and antimatter existed in perfect balance. They would annihilate each other, leaving a sea of pure energy and no galaxies. Yet our cosmos is dominated by matter, a puzzle known as the baryon asymmetry. According to the Standard Model, the early hot fireball should have produced equal amounts of both, but observations show a tiny excess, about 1 part in a billion, was enough to survive and form everything we see. Theories such as leptogenesis and CP violation in neutrinos attempt to explain this imbalance, but definitive proof remains elusive. Experiments at CERN and elsewhere continue to search for subtle differences in particle behavior that could tip the scales. This asymmetry set the stage for stars, planets, and life itself. Coming up, we'll examine why the universe's gravitational waves are quieter than many expected.
Unexpectedly, the primordial gravitational wave background, ripples in spacetime from the universe's first fractions of a second, has proven far more elusive than theorists hoped. Inflationary models predict a faint spectrum of these waves, which should leave a distinctive B-mode polarization pattern in the cosmic microwave background. Yet despite increasingly sensitive measurements by BICEP, Keck, and the South Pole Telescope, the signal remains below detection thresholds, forcing scientists to tighten constraints on inflation's energy scale. Some propose that the inflationary period was gentler than originally thought, while others suggest alternative mechanisms entirely. This silence forces a re-evaluation of how the universe expanded so rapidly. Next, we'll delve into the mysterious substance that still dominates the cosmos without ever being seen directly.
Hidden within the motions of galaxies and the scaffolding of large-scale structure lies a substance that never emits light, dark matter. Accounting for roughly 27% of the universe's energy density, its presence is inferred from gravitational effects, such as flat rotation curves of spiral galaxies, and the lensing of distant quasars. Yet after decades of underground detectors, collider searches, and astronomical surveys, no particle candidate has been confirmed. Some theories invoke weakly interacting massive particles, WIMPs, while others suggest axions, sterile neutrinos, or even modifications to gravity itself. The mystery persists, shaping research agendas worldwide. Consider how this invisible mass set the stage for the cosmic web we observe today. In the next segment, we'll explore how the inflationary epoch required an almost absurd fine-tuning to work.
Consider the inflationary burst that stretched space by a factor of at least 10 to the power of 26 in less than a trillionth of a second. For that rapid expansion to produce the smooth, flat universe we see, the underlying scalar field's potential must be exquisitely flat, a condition that seems statistically improbable without an underlying principle. Small deviations could have yielded a universe riddled with curvature or extreme density variations, preventing galaxy formation. Researchers propose mechanisms like eternal inflation or multiverse scenarios to explain this delicate balance, yet none have been empirically verified. This fine-tuning underscores how a minute shift in early universe physics could have derailed the cosmic story entirely. Intriguingly, the next item reveals a subtle mismatch in the cosmic microwave background's acoustic peaks that hints at new physics.
Intriguingly, the pattern of temperature fluctuations in the cosmic microwave background, often described as the universe's primordial sound waves, doesn't align perfectly with predictions from the simplest lambda CDM model. The heights of the second and third acoustic peaks, which encode the density of baryons and dark matter, show slight deviations that suggest either additional relativistic particles or early time interactions we haven't accounted for. While the discrepancies are modest, they have sparked proposals ranging from extra neutrino species to early dark energy. Each hypothesis attempts to reconcile the data without overturning the broader framework, but none has yet achieved consensus. Meanwhile, a growing tension in the measured expansion rate of the universe adds another layer of intrigue. Up next, we'll dissect the Hubble tension that has divided cosmologists.
Meanwhile, two of the most precise methods for measuring the universe's expansion rate, observations of the cosmic microwave background and distance ladder techniques using Cepheid variables and supernovae, yield values that differ by about 9%, a discrepancy known as the Hubble tension. The early universe estimate from Planck suggests a rate near 67 km per second per MPC, while local measurements point to roughly 73 km per second per MPC. This gap could hint at new physics, such as early dark energy, or systematic errors in one or both approaches. The debate has galvanized a new generation of surveys, including the James Webb Space Telescope and the Vera C. Rubin Observatory, hoping to resolve the conflict. Strikingly, this disagreement also ties into another long-standing puzzle from the first minutes after the Big Bang. Coming up is the lithium problem, a chemistry conundrum that still perplexes scientists.
Strikingly, the amount of lithium-7 observed in ancient stars is about 3 times lower than predictions from standard Big Bang nucleosynthesis models, a discrepancy that has persisted for decades. While hydrogen and helium abundances match theory remarkably well, lithium's shortfall suggests either unknown nuclear reaction rates, stellar depletion processes, or physics beyond the standard model, such as decaying particles that altered early element formation. Laboratory experiments continue to refine reaction cross-sections, yet the gap remains. This inconsistency reminds us that even well-tested cosmological models can hide hidden flaws. Perhaps the most fundamental issue lies even earlier, in the uniformity of the cosmos itself. Up next, we confront the horizon problem that challenges our understanding of causal connections.
Perhaps the most puzzling of all is the horizon problem. Regions of the cosmic microwave background separated by more than 60 degrees appear nearly identical in temperature, despite never having been in causal contact under a simple expanding universe model. Inflation offers a solution by positing a rapid expansion that stretched a tiny, uniform patch to encompass the observable universe, but the exact mechanism and trigger remain speculative. Alternative ideas, such as varying speed of light theories, have been proposed but lack broad support. The sheer uniformity we observe forces us to accept that something extraordinary happened in those first fractions of a second. Finally, we arrive at the ultimate cosmic misstep, the singularity at the universe's birth, where our physics simply breaks down.
Finally, at the heart of every cosmological model lies the initial singularity, a point of infinite density and temperature where general relativity ceases to describe reality. This theoretical construct signals that our current laws of physics are incomplete, requiring a quantum theory of gravity to resolve the paradox. Various proposals, from loop quantum cosmology's bounds to string theory's pre-Big Bang scenarios, attempt to replace the singularity with a finite, well-behaved state. Yet no consensus exists, and experimental verification remains out of reach. The very existence of this breakdown is the most profound mistake in our understanding, reminding us that the universe's origin is still an open question. As we've seen, each of these 10 cosmic slip UPS reveals how delicate the early universe's choreography was, and why every new discovery matters.
Reflecting on these 10 cosmic missteps reminds us how fragile the tapestry of reality truly is, tiny quirks that could have derailed galaxies, stars, and even life itself. By following these stories you'll see why every new discovery matters, and you'll be ready for the next mind-bending list we drop each week. Subscribe now so you never miss the next deep dive into the universe's biggest mysteries. Which of these 10 mistakes surprised you the most? Share your thoughts below, and if you enjoyed the journey, please give this video a like. Your support keeps the exploration going.